Okay, so we are looking at this local search. And we have seen that it leads us to a problem of local maxima, because the algorithm does not have access to the entire state space. It could get stuck, it could only see some options and not all options, and could get stuck there essentially. So, we want to see how to get around. So, and we saw that the terrain which this algorithm is sort of navigating is determined by the heuristic function. Well, actually it is determined also by the move gen function, as we will see in a short while. Because given a set of states, it is a move gen function which tells you from which state you can go to which other state essentially, and we will see that we can play around with that as well essentially. So, I want to now introduce this problem today, which well known problem you are familiar with no doubt, called satisfiability problem. I presume everybody is familiar with satisfiability. So, we will just do a quick recap, that there is a formula, and we will assume for simplicity that this formula is in conjunctive normal form. It does not have to be, and but it is in conjunctive. So, it is a Boolean formula, you can say. So, something like A or B and A or not C or B and so on. A formula like that, where A, B, C, D, E are Boolean variables which can take two values, either true or false, and the semantics of and or is defined and not is defined, and we want to find valuations for A, B, C and all the variables such that the formula evaluates to true essentially. So, that is a satisfiability formula, which says that can you find values for all the Boolean variables such that the overall formula evaluates to true. And obviously, you can see that this is a kind of a search problem. You can say something like you start, then you say A is equal to true or A is equal to false. That is one way of looking at it, that you pick a variable, assign a value to it, pick another variable, assign a value to it, and you would generate a search tree in the process. Or you can say you can have branches for B at this end. So, you can formulate it as a search problem at various stages essentially. What we want to do today is a different way of exploring the space. Now, what is the space? The space is, so let us say we have variables are five variables. So, we have some formula which is constructed over these 5 variables. What is a space? The space is for each variable A or B or C or D or E a value of true or false. So, 2 raised to 5 possible states in this case. So, if you have n variables, then we have 2 raised to n states. What if n equal to 100? So, it is a similar problem, that if you are dealing with a large number of variables, then this problem could become hard, and in fact, you know that SAT problem was the first problem which was used by Cook to talk about NP completeness essentially. For n is equal to 100, we have 2 raised to 100, which is about 10 raised to 30 states. And so, we have about 10 raised to 30 100 bit numbers essentially, and we have seen earlier that we cannot trifle with numbers like 10 raised to 30. It is a huge number. It will take you billions of years to search through all these things, even if you could inspect a billion states in a second essentially. So, we have seen that argument earlier essentially. So, it is a difficult problem to solve. Of course, you must be familiar with the fact that there are variations or special classes of SAT problems, which for example talk about the length. So, this is called a clause and each is called a literal. So, the number of literals in a clause actually is characteristic of how hard the problem is. So, there is a variation called 2 SAT, which means that there are only 2 literals per clause. You can have as many clauses as you want, but only 2 literals per clause, and you can have as many variables as you want. But if there are only 2 literals per clause, then the problem is actually quite easy to solve, and some of you must be knowing there is a well known algorithm called Davis-Putman method for solving 2 SAT essentially. But 3 SAT is NP complete, which means the moment you go from 2 to 3, that you allow 3 variables per clause, then the problem becomes NP complete essentially. So, we want to explore something which we will call as solution space search. Which is not radically different from what we call as state space search, but except for the fact that we will in the search space every node will be a candidate solution essentially. So, for example, for those 5 variables my state could be something like this 1 0 1 1 1, and it is a candidate solution, which means that I am thinking whether if I put A equal to 1 meaning true and B is equal to 0 and C, D, E and E equal to 1, will my formula be true or not essentially. So, this is a candidate solution, and we will look at a process of perturbation. Which means we will take a candidate solution and perturb it to give us a new candidate solution, which is not, as I said, not radically different from what we were doing earlier. The earlier methods could be called as constructive mechanisms, where you assemble a solution piece by piece. So, that small diagram that I have drawn on there is illustrative of that, that first you choose a variable A, then you choose a variable B, then you choose a variable C and so on and so forth. But we are not doing that here. We are saying that we will take all the variables at one shot, take that as a candidate, and if it is not a solution, we will do something with this candidate to generate more candidates essentially. So, in that sense we call this a solution space search. Again I would say it is not radically different, it is just a different way of looking at things essentially. Even in a, for example, city route finding problem, you could say that if I have to go from IIT Madras to Marina Beach, the path from here to Adyar, is that a solution or not? You can think of it like that also as a candidate in some sense essentially, but here we are saying that we have all the values for all the features or variables that we can talk about. So, another example is the n queens problem. You can have a constructive solutions for the n queen problems. You can say place the first queen, then place the second queen, then place the third queen, and you can build the solution step by step, or you can say that I will have a candidate placement for all the queens. So, for example, in n queens you might say, so let us say 6 queens, I could say that this is a candidate 6 1 3 4 5 2, and I would interpret this as saying that that this is the first column, this is the second column, third column, and so I am saying the first column queen is in 6th row, the second column queen is in the first row, the third column queen is in the third row, and so on and so forth. So, this is my candidate solution, and I will do something with this, maybe I will do a permutation of some sort to generate other candidate solutions. So, that is a solution space way of looking at things, not radically different, but it sort of helps us to visualize the space a little bit differently essentially. Now, Remember that for this problem there are 2 raised to n possible states essentially, and what a move gen function should give us is how to navigate this space essentially. So, one way we can devise several move gen functions essentially for this. So, one simple, so we will call them as follows. I will call this a function n1 which says change one bit essentially. If you look at this notation where the candidate is a bit string, you are allowed to change one bit, so that I have neighbors like 0 1 0 0 0 sorry 0 0 1 1 1. So, I have changed the first bit, then 1 1 1 1 1, I have changed the second bit 1 0 0 1, I change the third bit here, so this is one move gen function that I have, or a neighborhood function. So, that is why I use the name n here. It is a neighborhood function, it given a candidate solution, it gives me a neighborhood of that solution, which is the same as what we call as move gen to start with essentially. Okay. So, back to our problem of local maxima. Why did we get into this hill climbing algorithm? Because we wanted to save on space essentially. Now, nowadays space is hardly a problem essentially. I mean, talking of computer systems, I remember that in 1990 I had a PC in the department which had 30 megabytes of hard disk, and the other day I was talking to someone and it said, oh, this machine has only 2 GB RAM essentially. So, so space is nowadays is not so much a problem. So, you might have heard essentially Bill Gates is famously supposed to have said at some point that who will need more than 64K of RAM. So, space of course has changed essentially. So, we should also adapt to the changing world essentially. So, actually before we come to this, there is a very simple variation to hill climbing, is why do you want to restrict yourself to only one successor essentially, why not more than one essentially. So, I will just illustrate that with a search tree, and as follows, that you start with a search, so start node, generate, let us say there are 5 successors for every node, maybe like this. So, you generate the 5 successors. Hill climbing says move to the best one. What is so sacrosanct about moving to only one? Why not move to 2 essentially? So, let us say I move to this one, or I consider both. I don't throw away the rest, but I keep these 2 best 2 ones essentially. Generate 5 children for this, 5 children for this. Again pick the best 2, generate 5 children and move on. This algorithm is called beam search, and this illustration has beam width is equal to 2. So, what have we done, that instead of hill climbing, which explore only one path in the space, we are saying we are allowed to explore more than one path simultaneously in space. So, in this example beam width as we call it is 2. So, this beam is like a, you can think of it like a beam of torchlight, you are shining it into this search space essentially. and you can have more than one. So, at every level we will have 2 nodes essentially. So, you will keep going down the search space, but you will keep more than one option available essentially. This is an algorithm which has been used very successfully in speech recognition. And you can imagine that it is useful in situations where there are a few options which are likely to be candidate solutions essentially. So, if you can keep more than one option. So, what is the problem in speech recognition, that you start with a speech signal, then convert it into phonemes, then syllables, then words and so on. Now, it turns out that very often different word combinations sound similar essentially. So, very often we think you said this or did you say this, right. We know that such a thing is possible. In fact, this book by Charniak and McDermott, in the chapter on natural language processing, they give an example of a woman who goes to New York and says, or a woman who comes from New York, I do not remember, and he says everything here costs a nominal egg essentially. So, what was she saying? What did the listener hear? The listener said costs whatever a nominal egg is. The listener thought that the woman is saying that everything here costs a nominal egg essentially. But what the woman was actually saying was costs what she intended to say was everything here costs an arm and a leg, but people speak with different accents and that kind of stuff. I am sure one of you can make both of them sound similar. I cannot do that so easily, but that is what she meant essentially. And what the listener heard was it costs a nominal leg. Now, you can see that this kind of a problem is actually very much the case in speech recognition, that people speak with different accents and the listener cannot always make sense of what. At the same time, the number of variation options that one has are not too many essentially, and an algorithm which can keep more than one option alive is likely to succeed in recognizing the correct sequence of words essentially. In signal processing circles, we call this a Viterbi algorithm essentially, which basically is beam search essentially. Now, what is the complexity of beam search? Space complexity, let us just consider that. It is still constant essentially, because the beam width is fixed. Instead of one node, you are going to keep b nodes at every stage alive, and so b times the number of neighbors is the maximum you have to deal with essentially. So, it is a constant space algorithm, but it may get around the hill local maximum problem, where one branch may not have a good successor, but for example, all these may be bad, but this may have 2 good successors. So, maybe somewhere here this solution will find, which would not have worked out if this was better than this. If this was better than this, only this would have been selected and only this branch would have gone, and it would have reached a dead end here, because we have kept 2 options, both these branches are there, and so it will work. So, that is one variation of how to get around this local maximum problem. But let us come back to this solution space SAT problem essentially. So, I want to talk about another algorithm, which is so remember that I said that, so this is a neighborhood function or the move gen function. It connects a given state, or in this case a given candidate solution, to other candidate solutions essentially. But why should I choose this neighborhood function? Now, just to recap, what does the hill climbing algorithm do? It generates all these 5 neighbors and picks the best amongst them. If it is better than this, it moves to that, otherwise it stays where it is. So, the complexity of the algorithm will also, so complexity of move gen function will depend on how many neighbors you have. We will have to keep this in mind essentially. I can think of another move gen function, neighborhood function. So, I will just call it n2 and it says change any 2 bits. So, n1 is says change 1 bit. Now, you can see that for this small problem of 5 variables SAT problem, this my n2 will give me a different neighborhood function. So, for example, one of the neighbors would be 1 1, or let me just change the first 2 bits 0 1 1 1 1. Another neighbor could be, I change first and third bit 0 0 0 1 1. It gives me a different set of neighbors. Not only it gives me a different set of neighbors, it gives me more neighbors. So, this n1 gives me 5 neighbors or n neighbors if n variables are there. This n2 gives me nc2 neighbors. In this example, that is 10 neighbors. So, it is a different neighborhood function. I can choose between different functions. How can I exploit this information? Can I devise an algorithm which will try to make use of different neighborhood functions? So, I can have n1, n2, then I can have n3 and up to n if I have n variables, in this case up to n5 essentially. I can say change all 5 essentially. Of course, that will give me only one neighbor and it will not take me far from there. Or I can have combinations. I can devise n1 2 which says change 1 or 2 bits or change up to 2 bits essentially, or I can say change up to 3 bits essentially, or n1 2 3, or I can go up to n1 n, which in our example would be n1 2 3 4 5. So, the first thing I want you to observe is that they are, if you go down this path, they are more dense. The neighborhood is more dense as you go down this set of neighborhood functions. So, I can't write this here. So, I can choose a sequence of neighborhood functions which are increasingly dense, which means they give me denser and denser neighborhoods. The most simplest or the most sparse is n1, which I can get by changing only 1 bit, and then I can get n2 which has 10, then I can get n12 which has 10 plus this 5 which is 15, and so on. I can create a sequence of neighborhood functions n1, n2, which is increasing density. How should I choose which neighborhood function to use? Remember, neighborhood function is same as move gen essentially. So, we have now the option of choosing a move gen function or neighborhood function, and we want to keep in mind that we do not want to get stuck in a local maxima in this case. So, what will be the heuristic function here? If I have a clause like this, or if I have a formula like this, h of n for a given candidate solution. So, these are all candidate solutions, right. How do you give them a value? Any suggestions? Number of clauses it makes true, that is the simplest way of doing it. So, we will keep that in mind. Or we can modify this to say weighted number. So, if a clause has more literals, then give it more weight. So, that is another possibility. But basically it gives you an idea of how much of the solution is solved in some sense. If I have 20 clauses and one candidate satisfies 7 and another one satisfies 12, then maybe the 12 is better than 7, I think. It is just a heuristic. Remember, heuristics are not perfect necessarily, but we will basically assume that the more the clauses, the better the heuristic function is. So, we want to now devise an algorithm which will search in this solution space and try to devise an algorithm which will not get stuck in the local maxima. So, what is the criteria one should use for choosing a neighborhood function? So, there are two things. One is that we want to also keep a leash on the time complexity of our algorithm. Is time complexity going to, are these going to affect my time complexity, or in what manner will these functions affect my time complexity? So, that is why I am saying, remember the hill climbing algorithm, what does it do? It generates all the neighbors and then picks the best amongst them and moves to that neighbor, then generates all the neighbors and does that. What about this function, this one? What is the neighborhood function here? Take this small example, 5 variables a, b, c, d, e, and this one is saying you can change any number of bits you want, change 1 or 2 or 3 or and when I say 1 or 2, I mean any 1 or any 2 or any 3 or any 4 or any 5. What is the neighborhood function? Entire space is a neighborhood function. Every node is connected directly to every other node essentially. You can move from any state to any other state in one step. How many maxima will this have? Only one, which is the global maxima, which is the solution. Okay, there may be more than one maxima, but that is not the point here. But what is going to be the complexity of the move gen function now? Remember that we said generate all the neighbors. Now, this is, if you are choosing this as a move gen function and using hill climbing, what are you doing? You are just doing brute force, saying generate all possible states and then pick the best one amongst them. Now, obviously, how many states are there? We have made an observation that there are 2 raised to n states essentially, and if the neighborhood has 2 raised to n state, then you have actually trivialized the problem and made it into a brute force search, which is no point solving, because 2 raised to n states is far too many to inspect anyway. So, this hill climbing algorithm, if you were to use this heuristic function, well, not for 5, but maybe for 30 or 40 or 100 variables, would not even start off. It would spend its whole life generating the neighborhood function. Obviously, we do not want that. So, what is the next best thing we can do? So, we cannot choose the densest function, that is what I am trying to say. Why are we interested in dense functions? Because dense functions will not have this difficulty of getting stuck in local maximum. What is the advantage of choosing a sparse neighborhood function? Faster. The neighborhood is generated faster essentially. And so remember that the hill climbing algorithm basically says generate the neighbors pick the best amongst them, if it is better move to that, then generate the neighbors and so on and so forth. So, what do we do? Can we devise a nice algorithm which will give us, which will allow us to see the sparser the algorithm, the neighborhood function, the lesser the states you are connected to, that is obviously the meaning of sparse. The more likely it is that you are not connected to a better state. The denser the algorithm, the more likely it is that for any given state there is always a better state, which the extreme example is this algorithm, because any state which is not an optimal solution or global maxima is connected to the global maxima. Every state has a better state, and the only states which do not have better states are the global maxima states. So, if you can try and imagine this, that choosing a move gen function is also devising the landscape. It is difficult for me to visualize it here, but it is what a move gen function is telling you is that one function is saying from here you can go to this to this to this to this or to this one. Another one is saying that from here you can go to some other set altogether essentially. And what is the notion of a local maxima? The notion of a local maxima is that this state is better than all its neighbors. That is the notion of a local maxima. If all the neighbors are the entire set like in that example, then it is a global maxima essentially. So, in another way of looking at it is that a denser function, if you choose a denser neighborhood function, then the probability or the likelihood of a state being a local maxima becomes lesser, because it has to be better than more neighbors essentially. It is just a very naive way of looking at it, but you can get some intuition out of that essentially. So, we would like to use a denser function because it is not likely to have states which are local maxima, which means the surface it generates would be smoother, and a smoother surface is more amenable to hill climbing essentially. If a surface has no local maxima, then you will reach the global maxima. So, there is a simple approach to, and it is given in this book which I mentioned. It is also given in my book, but I first read it here, which is how to solve it by modern Mikhailovich and Pujol. And you should really go and look at this book, because at the beginning of every chapter they give a nice interesting puzzle that you can solve essentially. Maybe one of these days I will give you one of those puzzles. The algorithm is simple, that you have access to a set of neighborhood functions and you do the following. So, I will just write it very briefly. Call hill climbing So, the meaning of this is, so I do not need the call also, right. We just say hill climbing. So, HC stands for hill climbing, hill climbing with the ith neighborhood function, and you put I is equal to 1 and then you put I equal to I plus 1 and put it into a loop. What is the meaning of this algorithm? So, you should work out the details. I am not going to write the details here. The meaning of this algorithm is, and depending on what is the resources allow, you will go into this loop. Once you run out of resources, you say okay, stop or something like that. But inside this is another loop, which is a hill climbing loop, and that is saying use the ith neighborhood function, and I am assuming that they are ordered according to increasing density. Use the ith neighborhood function, and when you terminate, when you come out of hill climbing, remember that we no longer have the notion of goal test. So, in practice, of course, you can put in a goal test check. So, for example, in a SAT problem, you can say yes, if all my clauses are satisfied, then stop. You can put in that extra check, but we are looking at optimization more generally now. So, we want to find the maximum value of this heuristic function. So, what we are saying is that start with the most sparse hill climbing, most sparse neighborhood function, climb up as much as you can. So, using the hill climbing analogy, then switch to a different neighborhood function, the next one, and climb up again, and then keep doing that using denser and denser neighborhood functions. So, if you can visualize this somehow, you can say think of the neighborhood function as giving you connections with ladders to from one state to another state or so on. So, each of them is a ladder, and if the ladder is going up, you climb up, if it does not going up, you stop essentially. And when you stop, now you suddenly get a different set of ladders, let us say these ones, and see if you have a better state, and then you keep climbing those different set of ladders and so on. So, what is the advantage? The intuition behind this is that you would do most of the climbing in the early stages, that your early sparser function will take you up quite a bit, and then when you get stuck on some local maxima, suddenly you have a different ladder which will take you to another maxima. This is the algorithm, it is called variable neighborhood descent. Well, they are talking about minimizing. So, it is imagine you are going down a valley instead of climbing a hill, or VDN. What this is saying is that use a sequence of denser neighborhood functions, and at each stage you do hill climbing essentially, and you can have variations on this and you can work out variations. For example, one could say that after having using N2, should I try N1 again or not, because now I am in a different state, maybe N1 will help from there itself. So, these are variations that you can try think of essentially, but the basic idea is simple, that if you are stuck on a local maxima, use a denser function and try that essentially, which means that depending on how much resources you have, you will exploit as many of these neighborhood functions as possible essentially. So, I just want to end with one example that we have discussed earlier, which is the Rubik's cube example. And what will the I want you to visualize what will the terrain look like when, let us say, you call an expert, and by an expert we mean not necessarily who will find an optimal solution, but who will solve it quickly according to a known solution. How will the terrain, how will that journey look like? So, the idea that I am trying to talk about is this, that this is a solution so which means what is a solution that move 1, move 2, move 3, move 4 and so on, somebody has given you a solution. How will the terrain look like given some heuristic function like the number of tiles in place or something like that initially, or the number of tiles out of place, let us say initially it will be some value which that are out of place, finally of course it should be 0, but how is the journey that is being traversed? And remember that we said, we made this observation that when you have partially solved the Rubik's cube, when you want to move further from there, you have to disrupt some of the earlier partial solution. That is reflected by saying that the journey is like this. Let us say you do like this and you have solved the top row, but now if you want to do the middle row, you have to disrupt this, but you will do something better, then like this, then there will be some variation, and then well, not so bad, maybe something like this. So, what am I trying to illustrate here is that if an expert is solving the Rubik's cube, then at each state on the way, if you were to plot the heuristic value, it would be something like this, which of course means that maybe this is an exaggeration, maybe it is like this or something like that. That real world problems are such that it is not so easy to devise heuristic functions which will generate smooth surfaces essentially. So, Rubik's cube is just an example of that, which means that I cannot even hope to solve Rubik's cube using a hill climbing like algorithm, because I will find it extremely difficult to devise a heuristic function whose surface would be monotonically decreasing towards the goal state essentially. In practice, since I have to disrupt the cube on the way, I will be forced to go against the heuristic function essentially. So, going with the heuristic function we will call as exploitation of the heuristic knowledge, and as opposed to exploitation is following the diktat. Somebody has told you do this and so you do that essentially. As opposed to exploitation is the notion of exploration, to explore new areas of the space essentially. So far our only attempt at exploration has been this beam search, in which we have said that we will keep many candidates alive, but in the next class when we meet we will see how to try to increase a component of exploration in search, and the reason behind that is that pure exploitation, which means purely following the heuristic function, is going to end up in local maxima. Even if the surface has local maxima, what kind of algorithms can we think of that will go beyond the local maxima and onto the global maxima if possible. So, I will stop here and we will take that up next week essentially.